Hi everyone, today I'm gonna record a second video of the Sigmoidal 1989, as I remember, theorem, and today is the main, I think, video of this little, I don't know, module or of like a group of videos, where we denote the main results of the whole paper, because previously we were discussing some properties and features of the theorem itself, how we're gonna prove something, what the theorem is all about, how to use that. Like, it wasn't said, but we inferred how can we use the results of this paper. But it was all abstract. We've touched a bit of what we're gonna be talking about today, but essentially we didn't do anything really mathematically. So today we're gonna do all of the math, like the most essential part again, because the theorem contains not only the second section but the third one, and it's not gonna be so interesting from my perspective. It's and results, like, don't really care about it, but again we're gonna read about it, because I don't think in results everything's additional is gonna be said. So today is gonna be the main lesson. Again, we're gonna do just as we did before. We're gonna read words together and break them down. And what I'm saying is that I'm not really into this theorem so far. I'm not into in the math part. So we're gonna break it down all together using like the internet and everything we can possibly use. So that's it. Let's begin. So let yn denote the n-dimensional unit cube from 0 to 1 in n dimensions, actually. So what I have already written is that this is our cube. I've written it in 3D. It's like 3D cube, this one, but again, it can be n-dimensional, but again, as you may understand, we can only draw up to 3 dimensions. So I could possibly draw it like that, so it's one-dimensional cube, but who cares about that? I could have just left like this part of the cube and say that it's two-dimensional, but again, who cares? We're gonna represent it in 3D, and then you're gonna get an intuitional understanding that it can be actually used for like a lot more spaces. But I think 3 spaces is convenient. 3 dimensions, I'm sorry. Yes, it's extremely convenient, so we're gonna work with that. The next thing is the space of continuous functions on Yn is denoted by Cn. Alright, I have already, because it's not the first time I'm recording this video, I have already denoted the space of functions. So this is the space itself, it's black. This is the space of functions, they're like blue. Alright. In general, and I was struggling with understanding of this thing, and we use those double braces to denote the supermum or uniform norm. And what is the supermum of the function? The supermum of function is the smallest real number n that is greater than equal of all of the values in the function range. In simple words, because I don't get that. The lowest possible ceiling that the function outputs values never exceed. So it's like a limit. The smallest upper bound of the values attained at the function of the given domain. This is the largest value that the function can... this is the largest value that the function can achieve. So what we're doing that, we can, by this property, let's do it like that, we can actually choose a certain function from our field. For example, this one. We can actually choose it. And what we can do is that we can I should actually draw it like that. We can actually find the supermum of it. Like that. It's gonna be the max it's gonna be like red. Yeah. So this is a maximum value of a certain function from this field. Alright, in general we use to denote the maximum of a function in the domain, yeah. The space of finite signed regular Borel measures on Yn is denoted by Yn. C for this thing, for representation of this and other functional analysis constructions that we use. Alright, I say no, like what is the Borel measure? Again, I'm not probably in mathematics specifically. Borel measure is a topological space that is defined for all open sets. It's a measure defined by Borel sigma algebra of a topological space, which is the smallest that contains all open sets. It assigns the size of probability. Alright, any measure defined on, yeah, in simple words. Because I don't know what is the topological. It's a way to assign a consistent size of length of probability to a very wide range of sets of topological space, specifically those. Alright, I get that. So what we do is that we can actually create a space that contains, I'm gonna do it like that. I think it's gonna be more good looking. Yeah, like that. And this one. Let's make it smaller. Yeah, like that. And so, oh, I'm sorry. What this thing will do? Ooh. Yeah, like that. We're gonna make it even more smaller. What this thing will do is that it's gonna be able to denote some certain functions, so we can actually choose. Yeah, let's make it like that. Oh, what it did. Yeah, those functions. Let's make them look like that. Yeah, so we have a certain amount of functions. In this space again we have a lot of them, so yeah, like that. But a Borel space or subspace, as I get that, is just yeah, it's gonna be a little long, I'm so sorry. I wanna represent it so it looks really great. Really cool. Yeah, it's gonna be a Borel space, yeah. So it's actually how is denoted? I'm from C, M from Yn. Yeah, it's gonna be yellow actually. Yeah, like that. Yeah. It's so hard. Yeah, like that. Let's just denote it without some complicated words. Another space of functions. And let's take all of those things a little bit farther. Yeah. It's another space of functions. Yeah, that's actually yellow, first of all. Yeah, that's it. Just in another space of functions. Borel measures, whatever. The main goal of this paper is to investigate conditions under which the sums of the form, we know this one from the previous video, are dense in C from Yn in respect to the supermom norm. What does in respect to the supermom yeah, it's gonna be yeah, it means that the size, distance, and convergence of mathematical typical function with the maximum absolute value that they attain. It's also known as a uniform norm, infinity norm, max norm. Is a main closed and bounded distance. What is the supermum known? Is the supermum known as same as the maximum norm? Okay, we don't care. It's not gonna. Yeah, it's probably gonna work. White nose integral. Not interested. I'm sorry. In simple terms, yeah, it doesn't work. Like that. Measuring its size by finding maximum absolute value over a given area rather than summing up over averaging it. So, oh yeah, I get that. I think I get that. So it's like, yeah, this probably, again, just as I got it, it probably means that this thing can actually let's like that. What we want to prove is that let's do it like green. Is that our like main thing, our main object is dense, so it's like everywhere in this cube. So it can be everywhere with respect to the supermum norm. I'm sorry. Is that we choose a certain error that so it can be like actually any error. So it's like if it's big, so the closest one is somewhere like that. So if we want to mimic this certain function, the supermum known, it's a certain like e that can be whatever value, and but it's not zero, like obviously, and it can be, so it actually means the distance, how close can we get to this function. So we can get really close, but the thing is that we will never actually create the function that is like the initial one. So yeah, that's it, I think. Alright, get that. Definition, oh, that's interesting. We say that sigma is discriminatory for a measure. Yeah, and yeah, this thing is also extremely important. Is that a measure? Let's actually take a bit of like draw more functions in a specific area. And so what it means basically is that let's say that those functions in this hyperspace, they have a certain property. So for example, that they're, I don't know, that they're linear, for example. And so if they have a certain measure that actually like makes them different from other functions, so we can create, let's choose a more fancy color, I don't know, like that. Yeah, so we can create a measure that actually separates those functions from others. And what it means, just an intuition. Yeah, and we're gonna take it mu. What that is, it's measure, aka like that, aka spotlight. Yeah. So what it possibly means is that let's do it like that. Yeah. So you have a certain measure, a certain spotlight. Why do you call it spotlight? Let's say we know that there exists a measure or a spotlight, just as I call it. It's not a mathematical term, it's just for a better understanding. Let's say that there exists a measure that can separate those, as we've stated, remember, linear functions, from all of the other functions in this space. Again, this space has all of the existing functions. So what we do, we have this measure, and how do we apply it? We apply it like that. So take the measure from this function. So we apply it to a certain function. We do something with that. It doesn't really matter what we do exactly, but we can apply it to functions. If we apply it to this function, what we would get? We would get 0. To this function, we would get 0. The 0, 0, 0, 0, 0. Or it's yeah, but what is a measure? And I just wanna make sure. Yeah, measures and functional analysis. Non-negative number to subsets. Yeah, I'm sorry, I was a little misguiding. Yeah, the idea is the same. Yeah, we can apply it to functions, but how it works? The actual measure that I was talking about was an opposite to the measure that we were talking about. What it means is that we have a certain measure. It's this color, like purple. Yeah, and we apply it to this function. For example, again, note that it's not in our subset of functions. We apply it to this function, it's 0. To this one, it's 0. To this one, it's 0. To all of the functions that are not in our subspace, it's 0. But if we apply it to this function, or those, all of them, it's not gonna be 0. So this is how it can actually distinguish certain functions with a certain property from other functions. So yeah, that's it. And the next thing is discriminatory. What we say, we have our sigma. We say that sigma is discriminatory for a measure, for a certain measure, for all y's, and yeah, implies that. We say that. Okay, that's cool. This is cool. What we're saying here is that, let's actually do it like that. We say that it's discriminatory for, yeah, like that. What we do is what we're saying, that this is the integral, the sum. We don't really wanna go deep into integrals, just understand what that is. It's the the area under the function. And basically about the measure, what I said, we use integrals when doing measures. As I know, again, I'm not really sure, but as I know, as I was reading about it long ago, we are just applying integrals. So what we do, what is it saying? That we're saying that it's discriminatory. It is discriminatory. I don't want to spell that. It's discriminatory if and only if and only if the measure that is blind to all of the sigmoidal functions. Again, let's say that this subspace was not a linear subspace. This was a subspace for only sigmoidal functions, and the only measure that can make all of them 0, that can actually distinguish between sigmoids and non-sigmoids, that can make all of them 0. The only measure, again, that exists must be 0. That's the key. That's the key thing, I think, for this theorem, is that the only mu that exists, it must be 0. That's it. Alright, so basically what it's saying is that I'm sorry, denote that like mu equal, if mu is 0, is actually worthless. It's blind to everything. So what we're saying is that we cannot create a mu that would be meaningful, that it's not 0, that would be able to distinguish sigmoids from not sigmoids. So that's a key thing, like you must understand it right now. Again, one more time. The only mu that can distinguish sigmoids from not sigmoids is 0, so it's meaningless. So there is no actually useful mu that can distinguish sigmoids from non-sigmoids. Alright, I think we've got this property right, I hope. Yeah. Maybe it's not all correct, maybe I'm just dumb, but whatever. We say that, alright, the next thing is gonna be easy. We say that sigma is sigmoidal if it has those properties. I'm gonna paste it. Yeah, like that. Oh, it's big. Yeah, you just our what it means by a sigmoidal function. Again, it may seem weird and complicated, but if you've seen the first video, the sigmoidal function is actually, as we know that, it's something like that. So yeah, basically when our value goes to plus infinity we get 1, when our value goes to to negative infinity, I'm sorry, we get 0. So that's it. 1 if t, we used x, whatever, is plus infinity, it's 1. When x is gonna be to negative infinity, it's a limit, so it actually goes to negative infinity, we're gonna get 0. That's it. Not complicated at all, isn't it? Alright, the first theorem, here is where we're gonna be cooked. Let sigmoid be any continuous discriminatory function. Alright, so we are saying that sigmoid is discriminatory. The infinite sums of the form, like this, what we were talking about in the previous video, are dense in C from Yn. In other words, given any whatever, blah 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 blah. That is what we were talking about. Again, so this theorem is gonna be actually the whole paper. It's everything, because what we are again saying is that the idea that we've been talking about for a lot of time, for like 2 videos, is that sigmoids are dense. So what it means, I'm actually holding the green color for something cool. Oh well, sorry again. So they're dense, they're everywhere. We can get as close as we want to any space of functions. Yeah, to any function. But to any space of function also makes sense. In other words, yeah, and we can make this error, I call it error because it's actually error, it's E. We can make it as small as we want, but it's not 0, it's more than 0. Alright, here's where it's gonna be complicated, I think. Let S. Alright, let's note our S. I think it's the time for a green color. Let's call them this is gonna be a little bit non-scientific, because I think, because I'm not really sure, I don't know, oh, what is that? Because I don't exactly know the properties of a discriminatory function. I think I probably can infer that the superposition of discriminatory functions is also gonna be the discriminatory function. But to be completely honest, I'm not sure, so for the sake of being entirely like true, being entirely sure, I'm gonna write these superpositions. But again, maybe it's not true, whatever. Let's just denote them as our favorite cube. Cause I like it, I like the representation. I spent like a minute on creating that, so I'm gonna be using it widely. Can I actually make it like, whoa. Can I actually make it a group like of things? I think you cannot. Whatever. Yeah, it's gonna be green. Let's note it as not oh, the same thing happened. Yeah, let's denote them not as something really big, but certainly bigger than the white one. Let's make them look like that. So those are our discriminatory functions, or sigmoidal ones. Alright, be the set of functions of the form S in 2 clearly as is a linear subspace of C. Alright, what is a linear subspace? Linear subspace in simple terms. That lives inside a larger vector while obeying all the same rules at larger. Yeah. What we're saying is that it just belongs here, just in the black cube in the our space. All right, we get that. We claim that the closure of S is all of C, whatever. The closure. What is a closure? Assume that the closure of S is not all of. I get that. So closure is actually everything that's inside it. And what he's saying, we claim that the closure of S is all of our subspace of functions, our C. So we claim that all of the functions are inside this green cube. So we assume that those and those should be exactly in this green cube. Yeah. Assume that the closure of, alright, we are going from from different perspective. We assume that it's not right. Then the closure of S, say, R. So what we're doing here is that we are assuming that it has I think I ran out of colors. Yeah, this one. What we're saying here is that it's not gonna look really great. Yeah, we have this that, the closure. It's R, the closure of it's R. Now let's call it in simple terms. Yeah, it's actually what's inside of us. Sorry. Yeah, and again, we're gonna denote as pink as the different closure. What's not actually in the cube. How it's called? Blah 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 blah. Let's call it, yeah, it's R, but yeah, we don't have that, but let's say it's a different closure of, I actually want to get rid of it. That's wrong idea to write to draw it. Alright, then the closure of SSR is a closure proper subspace, like a subspace, obviously it's a subspace. By this guy's theorem, I don't know who that is and I don't really want to dive in his theorem. There is a bounded linear functional on C, call it L, with the property that L is not 0, but L from R equals L from S is 0. By the boundaries of the form, for some mu, for all of them we must have that. However, we assume that is discriminatory, contradicting our assumption. Yeah, that's sorry, I think I've got it. Because they are actually talking about a very uncomplicated thing. They are using clear math terms. We are using practical ones because we want to understand the theorem. Is that, yeah, I think I've got the idea. So let's firstly break down the idea, and then we would probably try to dive in the math, but I don't think that it's really necessary because the whole idea, we understand that. Alright, so what we're saying here is that one guy says that he has actually created a theorem that tells us that there exists a mu, a measure that what we were talking about is that for all of them it's 0, but for all of not them, let's call it not them, it's not 0. And what it's saying, do you get that? We've assumed that this is discriminatory, and the only mu, this is 0 to all of them, is 0, but this guy says that it's not 0. There is a contradiction. That's it. Yeah, so this bounded linear function is of the form whatever, this is the definition of the functional. For some mu, for all of the functions that belong to this thing, in particular, since it's an R for all of the, we must have that. Alright, you must have that all of the sigmas are 0. However, we assume that it's discriminatory, so that this condition implies that mu equals 0, contradicting our assumption. Hence, our subspace must be. Yeah, so we've defined this thing. It's an integral as I was talking about. Yeah, and we're like this guy. This is literally his theorem. This is literally the practical use of his theorem. However, we assume that this is discriminatory, so that this condition implies that mu equals 0. Yeah, contradiction. This demonstrates that the sums of the form, just as we were talking about, are dense in C from Yn, providing that sigmoid is continuous and discriminatory. The argument used was quite general and can be applied in other cases as discussed in section 4. Now we specialize this result to show that any continuous sigmoidal discussed before, any continuous sigmoidal of the form discussed before, namely, is discriminatory. It's worth noting that in neural network applications, continuous sigmoidal activation functions are typically taken to be monotonically increasing, but no monotonically is required for OWL. Alright, we've just proven that, but you probably see the abstract, see how artificial our theorem is. Is that okay? We say that it's discriminatory, but we didn't actually prove that it's in reality discriminatory, so we're gonna do that. I think. All right, so we didn't get all of the things to work on. All right, this lemma is actually telling us that we're gonna prove that our sigma is discriminatory. All right, to demonstrate this, we have our sigmoid is 0. Yeah, we are actually rewriting this, multiplying it by, I don't know, this letters for alpha, probably alpha. All right, we have that it's 1 if alpha is plus infinity. All right, if it's like, if the weighted sum is more than 1 and it's plus infinity, so it's sigma from plus infinity is 0, an opposite thing, and it actually the sigmoid from this thing for all of the sigmas. All right, cool. Let's actually screenshot that property, because I think it's gonna be interesting, and it looks like I'm cool. All right. I like that. The property. Yeah, like that. It's gonna be the property of it. Like that. I know where to pass it, like that. Alright, thus the function, yeah, converge pointwise and bundle it to the function. Oh, okay, that's interesting. We are just changing the function itself. What does it mean? We have this sigmoid function on the top here. We have some conditions of this function which are true. Then we are saying that there is another function that looks, so far it just looks easier. I don't know how we're gonna use that, but it has the same property. It converges pointwise, so every point of it is same as the point of this one, and boundedly, so the bounds are exactly the same. I think I'm breaking down the easiest things very well. I don't know why. Yeah. So like, why does it the same? It's 1 if this thing is more. All right. It's 0 if this thing is less. This property is not changing, so whatever. And yeah, cool. I'm not really sure that we can get rid of this lambda. I think it's more like lambda or alpha. No, alpha is different. Alpha is like a, lambda is like, I don't know. Let's call it lambda, whatever. Alright, we're changing this function. Not really sure we can do it, but it seems so. Yeah, I've missed that. Yeah, as lambda is gonna go to, it's limited to plus infinity. Yeah, so if this property is true, alright, it's all entirely true. We believe that. Let P, uppercase P, I don't know, be the hyperspace defined by this thing, and let H be the open half space defined by, yeah. By this convergence theorem, we have that. I don't get that. Alright, we are saying that we actually break down this, like it's a hyperplane, and we are breaking it down. We are defining it as like what it actually does, it actually like breaks the space to a half, basically. So it's like 1 or 0, or this weird thing. I think it's in the middle somewhere, like. Alright. Oh no, yeah. We're breaking it down to a half space, where one half is defined by this property, it's 1, another half is whatever. Then by the theorem of this guy we have that there is a measure for this thing is 0, is the same measure for this thing at 0, and it's equal to this thing. Yeah, so this guy is basically saying that we can rewrite our measures in the form like that. So if there are two functions, if the measure exists and it's 0 for those functions, so we can rewrite it as the first function by a measure plus the measure of the other hyperspace. Yeah, so what he's basically saying that if a function can be, I don't know about this property, but basically if a function can be divided into like two hyperspaces, probably. Like half spaces, I mean. So we can rewrite it this way. Alright. Yeah, he's basically saying that like those functions are the same, and I don't know why we actually use this function. It's not used here. Like, okay, maybe for the sake of the theorem, but we get that we have this thing, and linear functional according to that is a bounded functional on since of finite. Yeah, I'm trying to define about why we're doing that. Let h be the indicator function interval, so yeah, like that. Similarly, then here he uses this Fourier thing. Okay, I get that. So what we're doing here is that we have this hyperspace trick. Then we're gonna do something, then we're gonna use the Fourier theorem, and like if it's 0, it implies that mu must be 0. Alright. We know that the measure of half planes being 0 implies that the measure of mu itself must be 0. Didn't know that, but let's say that it's a trivial theorem. This would be trivial if mu were a positive measure, but here it's not. Okay. Fix y for a bound measurable function h, define the linear functional f according to this thing, and note that f is a bounded functional on since a finite sanct measure, let h be indicator functional of the interval, that is h from and u is more than that, so that Alright, so what we're doing here is that we're defining some kind of functional, and we're saying that this functional implies that the sum of those two functionals must be 0. Okay. If only they're positive, as you get. Yeah. Similarly, open interval by linearity. Hence, any simple function that is in the self indicator simple sum. In particular, we wanted to measure. Alright. So he has basically defined this thing, and then Yeah, I think we can skip that. Like 0 if in the indicator of the function an open interval by linearity for the indicator function of an interval, and hence for any simple function that is the sum of indicator. Since simple functions are dense, f is 0. Yeah, so this is the actual proof, but this is a better proof. Yeah, he uses Fourier transform. Yeah, and by the Fourier transform we have this exponent which is not 0, and by this thing it's 0, so this mu must be 0. For all of the Fourier transform of mu is 0, and it must be 0 as well. Hence, alright, cool. So the only thing that we're struggling right now is that is that we don't really understand. Is that we don't really understand that we understand that we have this some kind of a measure again, stating the properties of this measure, and know that it's a bounded functional since it's a finite signed measure. So he's using so what we're basically doing is that he's creating a measure and then using the Fourier theorem to prove that it's 0. And what's important for this thing is that the measure that he can use, he's basically using that for like half space functions. So if the function is like actually breaking down the space into two parts, so it's discriminatory. It's what I understood from it. But the essential properties that he gives to his functional are not really understandable for me so far. And to be honest, I don't really wanna dive in. No, I think I should probably use. I should probably do. Since a finite signed measure. We now show that the measure of half space planes being 0 implies that the measure of it must be 0. This would be trivial if positive measure. Alright, so we're saying that it must be 0 if mu is positive, because if it's negative, obviously this sum may be 0 as well if mu is not 0. Fix y. Alright, we are fixing that. For a bounded measurable function h, for a function h, define the linear functional f according to. He defines a functional for a random function, for a bounded measurable. And note that f is a bounded functional on this thing, since mu is a finite signed measure. Noting some property of f. Let h be the indicator function of the interval. Yeah, so we're creating an indicator function for this interval. That is, alright, an indicator, just understand what an indicator is, we don't need to break it down. So that, that's it. So, what we're doing here is that we actually have a function that has a certain properties, that is actually half space related thing. What we're doing here, then we're creating an indicator that would actually separate half spaces. Then, by the theorem, we can see that an indicator that by some person, I don't know, we can say that this property is true. Similarly, f is 0 if h is the indicator function of the open interval. Alright, probably, I don't know. By linearity for all the indicator function of any interval, and hence for any simple function, that is the sum of indicator function of intervals, since simple functions are dense. Yeah, we're saying that, okay, like they're dense, so we're actually proving something. I feel that this is not actually important. This is what's important, because we use that the bounded measurable functions, and those functions give this thing. For all. Mm-hmm. Mm-hmm. Actually, love the sigma itself. Yeah, here where we have that. Mm-hmm. Mm-hmm. For all okay, so there is a property of f of h is that it's related to our sigmoid. Then and only then we are saying that now we change h for any function that is bounded measurable, so it has the same properties. And then we're using the Fourier theorem. Alright, the basic idea is understandable. So yeah. I'm just trying to comprehend that. Cool. Decent. Okay. We have this property. We have this property. And yeah, for bounded, let h be bounded measurable. Yeah, so we're saying that for any indicator this thing works, and yeah, I think I got that. So this is the indicator, and we're saying that for any indicator it works, and because of any indicator it works, this is essentially, I think, the indicator itself, and this is the same as this one. So this is why the sigmoid is discriminatory. I think that's the point. I think we can move on. Maybe, yeah, I think we can move on. I think the only problem is here is in this part, in this passage. Actually, this one is understandable. Yeah, one last time, we now show that the measure of half space planes being 0 implies that the measure, okay, yeah, I get that. Fix y for a bounded measurable function h defines the linear functional f according to. Cool. And note that f is a bounded functional. Don't know what is a bounded functional, since mu is a finite signed measure. Let h be the indicator function of the interval. We're breaking it into half spaces. Yeah. Then we're saying that this must be true. Similarly. Bilinearity is indicator. Yeah, especially this thing, bilinearity f from h is equals 0 for the indicator function of any interval, and hence for any simple function. Okay, the whole idea is understandable. It's cool. I think it's an hour video. We can move on because we actually understand the point of it. We understand basically how it's done. Maybe we would probably dive more into like even more advanced math, but I think it's understandable that we were talking about today. We have the basic idea of how it's proven. I think it's profitable. I think it's cool. So like, thank you for your watching, and thank you for the fact that you watched the video. I'm sorry, I'm losing words. And next we're gonna work on the applications. It's not really complicated. There is another theorem. Okay, results. Cool, that's it. And 5 theorems. We only have like 5 of them. And summary, don't really think we're gonna care about the summary, but well, so thank you for watching actually.